So we are now live. You should see that your off air button went to on air. And so people are probably in the process of refreshing their screens and uh, hopefully tuning in as we speak. Fraser and I have learned to give people a moment to click into the Hangout. Waiting for an audience is always the fun part. We'll go ahead and get started in a moment. I'm going to share this out. Do you have any audiences that you want to tweet this out to while we get started?
Actually, I'm not a big Twitter. I don't tweet. I should
That
do.
it's totally all right. Not everyone is into Twitter. We have a huge audience who watches later, so if we don't have a live audience, that's fine. Since we don't have one right now, I am going to take a moment because I can edit off this part right here.
Okay.
I'm going to go ahead and work to share this out via a couple of different sites to see if that helps. Unfortunately, since the semester hasn't started yet and we're currently competing with AAS, that takes a toll on things. Yeah, Twitter is a fabulous place, assuming they don't decide to turn it into 10,000 characters instead of 20,000 characters, instead of 140 characters.
Right. I've heard about, yeah.
Okay, 2 more shares and I will have exhausted what I can do.
So when people come on, we'll basically ask.
I can see them on my interface and they can ask questions through text.
Gotcha.
So it's just like having a producer on a radio show, and a lot of the bigger podcasts where you have rapid fire questions from hundreds and hundreds of people at once, they'll have a separate producer. We're not quite that big live. Like I said, more people are watching us asynchronously later.
Okay.
Okay, well, I have shared to the best of my abilities. We have viewers! We have viewers again! Yay, viewers! Okay, this is very exciting. It's always good to have viewers. I'm going to go ahead and get this started now that I see people are out there live watching us. Thank you for joining on a weird night. Hello, everyone. This is the Center for Lunar Exploration podcast, Center for Lunar Science and Exploration podcast. We are here tonight with Bill Farrell, who is the director of DREAM2, which is a NASA program that looks at the atmospheres of all of those little rocky things that you probably forget have atmospheres. So we're talking about asteroids, the moon, which isn't so much of a little thing, the moons of Mars, Phobos and Deimos, and trying to understand how it is that these bodies' environments respond to all those things that are going on in our solar system. This is a fabulous new program that has an absolutely fabulous name. Could you give us an overview of what it is and how you got started?
Sure. Yeah. Uh, should I go?
Yes.
Yeah. Good. Yeah. Well, actually, what DREAM stands for is the dynamic response of the environment at asteroids, the moon, and the moons of Mars. And what we're really looking at is how the various elements of the space environment affect these airless bodies. And for example, the sun gives off the solar wind, an energetic plasma. And for an exposed airless body, it's just directly immersed in this flow. And as this plasma flows around these bodies, it actually can develop a wake behind the body, just like you do a boat wake. You can develop some of this solar wind plasma actually implants into the bodies.
So, what does implant mean for someone who might be thinking spring plants right now?
Oh, well, actually, what it really means is that the ions, see, the solar wind are really protons, hydrogen ions, and they'll go in and embed themselves into the top surface of the soil.
So it's literally these charged particles coming from the sun are planting themselves into these different worlds.
Into these, exactly, exactly. So it's almost like a sun airless body connection. It's really an electrical connection since it's a plasma and a charged gas. They're linked, and it's not just the solar wind. Micrometeorites are constantly gardening and bombarding the surface. So they come in and they whack the surface, and when they do, it releases neutral gases. It releases a little puff of ions. So you have particulates coming in at 20 kilometers a second, just slamming the surfaces. So the moon is a good example where you see the big craters, but at the smallest scale, at sub-millimeter scale, there's almost like a constant raining of meteors, just like our meteors, like in our atmosphere. We have meteor showers, and throughout the night we get bombarded by meteors. Well, the same thing is going on these airless bodies. There's not an atmosphere to speak of, so they come in and they just hit the surface directly.
So let's try and take this back and just break it down into small pieces, because this is
Right.
amazingly exciting science that a lot of folks don't know about. And those of you who are out there watching us live, don't be afraid to stop and ask us questions by clicking on that little yellow Q&A app button that is in whatever window it is that you're watching us live in. So as I understand it, our ever active sun, and this is a highly active time right now. This is why we're seeing so many fabulous aurora here on Earth. Our sun is releasing these high energy particles that are part of why we see this aurora activity. Here on the surface of our planet, we have a magnetic field, we have an atmosphere. All of these things react together to make the colorful aurora. But with the moon and all of these other bodies that don't just not have an atmosphere, they also don't have the same giant magnetic field the Earth has.
Right.
These particles plow into the surface. And when this happens, when they give their energy up to the surface, you get all sorts of different things happening. And you're studying what these things are that are happening.
Right. In fact, the analogy I like to use is imagine you had an old carpet. Imagine the lunar surface has the history of the moon going back 4 billion years. Well, in some sense, your old carpet in your house has the history of your family, the cats, the dogs, when you spilled juice, all that stuff. Well, imagine you took your carpet and you wanted, how you clean a carpet, you hit it a couple times and you see dust come off and you get this strange odor. Well, in some sense, that's what the space environment is doing at the moon. I mean, these micrometeoroids, solar wind, charged particles, all of this energy kind of at the microscopic level is hitting the moon, and the moon responds by releasing neutral gases, releasing its own ions. Basically, you can actually get a charged, a dust exosphere, a chunky gas, almost like an atmosphere around the moon itself. In fact, that's one of the recent results found by the LADEE spacecraft that flew around the moon, is that the moon actually has a basically suspended, well, not really suspended, but lofted dust up as high as a few hundred kilometers from the moon, really generated from these micrometeorite impacts. Micrometeoroids come in and secondary ejecta is released, and in doing so, you have this material, particulates, surrounding the moon that LADEE detected.
That is perhaps. Go ahead.
Oh, well, and not only that, but there's also gases released. So there's sort of a low density atmosphere called an exosphere. And then there's this particulate component. So what we're finding is that the moon actually has this, it's not just a solid body, but above it for a couple hundred kilometers is this combination of gas and dust. Low densities, of course, but it's surrounding the moon. And it's constantly generated and by this incoming energy.
And one of the ways that this works is you're dealing with, like you said, these are low gravity environments compared to Earth and things that are clearly bigger than us. And these are environments where you don't have a lot of reason for the dust and particles to fall out of this exosphere. So here on Earth, if you've ever gone out on a really dry, dusty day, if you ride around on a bike, if you ride around on a horse, which is what I tend to do, all of this dust gets lofted up into the air and it eventually falls out due to humidity, falls out due to weather, and it doesn't build up charged particles on it because there's lots of ways for it to get neutralized. But especially where you're looking at the moon, a lot of these particles are getting hit by ions, as you pointed out, and they're building up an electric charge. And you have all of this stuff getting levitated, and it's trying to repel each other because of that electric charge, if I understand everything correctly. And all of this works to create a not wanting to fall back down kind of dusty bad day.
Well, yeah, it's definitely the electrical environment at the moon is different than anything here on Earth, because in fact on Earth where the air is actually an insulator, on the moon the plasma is actually a conducting medium. So in fact you're immersed in a conductor. So if you're in the solar wind, one of the questions we've been asking on DREAM, though, is what happens when you go to the lunar night side, when you're no longer directly in the solar wind and you're in this wake region where the solar wind is blocked. Well, now you're no longer in that electrical conducting gas. So now what can happen is if you charge up by walking around or with a rover tire, it's actually harder to dissipate the charge in these shadowed regions. So we've actually been talking about this a little bit as NASA has been trying to think about exploring these lunar polar craters, like during the Resource Prospector mission that's coming up. They maybe want to go into a shadowed crater up near the North Pole. And if they did something like that, they would actually sort of temporarily be out of the direct plasma flow. And if they charged up, now the question is, where do you dissipate that charge? Because the lunar regolith itself is actually a fairly poor conductor, particularly the cold regolith.
It's basically silica, isn't it?
It's basically silica, right? And in fact, it's a semiconductor, and as it gets cold, the electrical conductivity drops right out. In fact, in some of the coldest regions, if you're in a deep polar crater where it's really cold, it's actually less conductive than paraffin. So it's really a sort of a super insulator in these cold regions. But then you're also in these permanently shadowed cold regions. You're also out of the direct stream of the plasma. So now you have no electrical ground to speak of. So that's kind of an issue that we go after in DREAM, is say, okay, where is the electrical ground? And what we're really trying to do is trying to understand this from a science perspective and then feed that information forward to our exploration colleagues who maybe do want to rove around in there someday, to say, hey, you maybe have to think about this a little bit. You might have to ground things a little differently, or you might have to have a plasma emitter because you might charge up. You have to handle charging a little differently than you would if you were on a spacecraft directly immersed in the solar wind, or if you were here on Earth, or even if you're on the surface of Mars. The environments are very different.
And this raises a whole lot of difficult issues for your poor little rover, because first of all, dust is evil. Right. Second of all, silica dust is sharp, scratchy, nasty. So it adds a whole new dimension to being evil. And now you've added static electricity on top of it. And I think all of us who live in cold climates with wool socks involved understand the problems with static electricity and electronics. And so there's a whole lot of science that you guys need to do to help keep the explorers safe. And what are the variety of questions that you're working to explore, and how do you do it when, well, we don't currently have rovers that you can get data off of?
Well, our DREAM2 team is primarily a modeling team. And so we use spacecraft data and data that's been collected, and then we apply it to our model. So a good example is we just had a paper, a colleague of mine, Talana Jackson, just published a paper this year on exactly this issue of a rover tire charging up, rubbing against the regolith and charging up. And then basically the hypothetical tire was placed in different locations on the moon. So what would happen if it was on the lunar day side? Well, as it turns out, there's a lot of photoelectrons. You're immersed directly in the solar wind. That tire would dissipate on timescales of a millisecond. But if you take that same tire that has roved the same distance over the regolith, and it's gotten charged up, and now you put it in the night side, it takes substantially longer to dissipate.
And so what this means in practical terms is dissipation is how long a capacitor, in this case your tire, holds on to the electricity. And if it holds on to it for a long time, that means you touch it, you get zotted even a while later. In an ideal situation, the charge goes instantly away and you're in no danger of getting zotted. So
exactly. The quicker you can dissipate that charge, the better, the safer the environment. And so, we're just curious, and then if you take that same tire and charge it up and put it in a polar crater, it can really be a problem. And in particular, if you continue to rove, it's almost like a Van de Graaff generator. You keep building up charge, and at some point there's going to be a breakdown. So the question then is, and that's the question we want to ask human exploration is, how do you want the breakdown to occur? Do you want it to, you better plan for that and think about that, because you don't want to be surprised by the breakdown. So anyway, so she has this paper out, just came out this year, just describing this exact effect, and dust sticking to the tire too at the same time.
This is every person who's lived in a wool sock wearing climate's worst nightmare. Now to do a quick station identification for those of you who are tuning in late. This is the Center for Lunar Science and Exploration Hangout, which we will be also distributing as a podcast on 365 days of astronomy. I know how many days are in a year. And with me is special guest Bill Farrell, who is the director of DREAM2. Now, any of you who are out there listening live, you can ask us questions by clicking on that little yellow Q&A app button. And I see that Kyle Carmichael has clicked on that button, and he's posted the question. Could the design of a robotic explorer or an astronaut suit create a charge to repel the dust?
Yeah, people have talked about that, as it turns out. One thing that a colleague of mine has discussed is maybe having a metal, basically have a metal outer skin. And we're actually working with the folks at Johnson Space Flight Center, trying to get that idea into the current suit designs. But a conductive spacesuit is attractive for a number of reasons. First off, you're actually, where you have plasma, you have enough area to collect plasma to help remediate charge buildup, because the larger the current collecting area, the more plasma you can pick up, and the more you can remediate charge that you've picked up from scuffing along the surface. But the other thing, a nice thing about a conductive suit, is if you wanted to repel it, you could, before you enter a space capsule, you could actually touch a voltage, a higher voltage system, and actually have your suit discharge the dust grains. That's been discussed. It's sort of a way of, or basically have a grounding stick where you touch. Not have to worry about the discharge itself, but you could find ways to remediate the dust that's on your suit. And if it's conductive, you can handle it all at once by removing charge through sort of a slow leakage grounding system.
I have this mental image of you're outside working all day, you come back absolutely covered in dust, you put your hand on the unlock the door but remove my dust please switch, and all of a sudden, boink, you're completely clean, thanks to the wonders of electricity.
Well, yeah, and back when maybe I want to say 2007, 2008, people have really talked about this kind of electrostatic curtain using electrostatic fields to remove dust. I think Kennedy was developing that. They may still be working on that at some
Not the
level.
person, the Space
Oh,
Center.
the Space Center. Yep, Kennedy Space Center. Yep, thank you. Um, and let's see, what was another thought? Oh, the only tricky part to this is that the smallest dust is not electrostatically bound. Once it gets near your,
It's electrostatic. It's electrochemically bound, actually,
it's
isn't it?
electrochemical. Exactly, it's a van der Waals force, and so the smallest dust is the hardest to get rid of. The stuff that's at 20 microns just sticks right in there, and actually that becomes a little tougher. Even you can't. It's sometimes even tough to get that to jump off. And that's always been the bugaboo with these electrostatic dust removal systems.
Yeah.
Other forces start getting playing a role there.
And we have another question coming in that deeply amuses me. The question is, so I have to ask, what is the unit of Zotting? And I have to admit, it's probably volts because it involves electrons jumping around. Um, so
Did
so
I say Zotting?
I said Zotting. I'm guilty of that.
Oh, okay. Oh no,
Um,
that's good. That's good. But we get it. We
yeah.
you can picture it. It's visual.
It's yeah, we've all experienced it at one point or another. So you're working on understanding all of the problems with dust, and you could probably write an entire book on the problems with just lunar dust alone. But you guys aren't just focused on our Earth's moon. You're also looking at asteroids, and people really don't normally think about asteroids other than maybe Ceres as having well, they certainly don't have sunset causing atmospheres, but they do have, again, that exosphere that you were talking about. And can you differentiate atmosphere versus exosphere?
Yeah, actually, I can. An atmosphere is collisional. Like what we have here on Earth, all the molecules collide, and there's pressure gradients. The way our weather moves are really gradients in pressure. In an exosphere, the path length between collisions is so large that basically the molecules and the atoms that are released don't collide. So in the case of the moon, they actually argon and some of these other atoms will be shot up from the surface, won't collide with others of its species. Instead, it'll come down and hit the surface again, and it'll be the surface interaction that actually gives the argon its energy. And when that happens, it's referred to as a surface bounded exosphere, meaning that the gas is really getting driven by the surface and not from gas-gas interactions.
And I know Mercury isn't part of the DREAM2 purview, but it's really my favorite example of this because there are certain views of Mercury, I believe with SOHO, that catch it at an angle and in the right detection wavelengths where you can see it has a trail of particles behind it, kind of like a comet, and driven in this case by, again, particles from the sun hitting its atmosphere and discharging material from the surface. And Mercury is actually getting smaller on a constant basis from this impact of light and particles from our sun. Now, Mercury is kind of a planet and easy to see. How do you detect this with asteroids?
Well, it's actually with asteroids, the exosphere there, particularly on smaller asteroids, probably is not actually bounded to the surface. So whatever is shot out is immediately released and doesn't hang around. So it's in fact the people what the exosphere specialists call it at small bodies when it's no longer bounded. They call it a corona. So it's a very, very tenuous emission. But again, if micrometeoroids are hitting it, these neutrals are going to be shot out. solar wind plasma. For every hydrogen that comes in, every 10 hydrogens or so, I think it's about every 30 hydrogens, you'll push out a silica molecule. So or pieces of silica, SiO2, either the S or the O's, via plasma sputtering. So these processes that are going on at the moon and that we understand at the moon, we're actually on DREAM asking ourselves, how do they apply at small bodies where the body mass and gravity is less? What does an exosphere look like as the mass, you know, in a limit goes to zero? You know, it just you know, and there's no gravity, and so now the exosphere just escapes. So these are the kinds of things that we're looking at with DREAM2 and trying to get sort of a universal understanding. In fact, in the last couple of years, one of our colleagues on DREAM tried to develop sort of a universal exosphere picture, where you could, in some sense, look as a function of mass and ask yourself, given mass and sort of the temperature of the gas, how much of it would stay bounded and how much of it would be released. And it was really, really interesting. I claimed actually he did such a good job, he was actually putting all the other exosphere scientists out of business, because it really was sort of an all-encompassing sort of view. Because a lot of times exosphere scientists just want to study this body and this body, and if you can, you know, but there is some universality to
Science is
this.
the same everywhere. We just need to figure out how to combine our boxes to get that bigger picture.
Exactly. So it was actually kind of a cool study, and then actually in just a few kind of color charts, you got a really interesting feel for what was going on. So again, that's another thing on DREAM2 we're trying to do, is sort of get not just the moon's view and a small asteroid understanding, but sort of fill in all the different
that continuity across different size objects.
Exactly. Same with the plasma flow. You know, as plasma comes in, some of it hits the surface, and then it goes around the body and forms a wake. For the moon, there's one kind of wake, but a decrease the size of the body, the obstacle in the solar wind flow, that's going to change the nature of the interaction. And that's, again, another thing we're trying to understand, from big to small, how does that interaction change?
And that makes sense for anyone who's looked at the differences in how different types of wings have different types of wakes.
Right.
Now, we have another question coming in from the audience, and I have to admit, I don't know the effect he's talking about. So we have Marcus Dupay. I hope I pronounced that correctly. I'm sorry if I didn't, Marcus. He's asking, does this help to understand the Yarkowski effect? Or Yarkovsky effect?
Yeah, the Yarkowski effect, right? Where you actually can start spinning up asteroids based on solar radiation, and that's actually a good question. Not directly, we don't actually study that effect. And then just to kind of outline what that effect is, what ends up happening is as an object is, particularly an irregular shaped object, is getting irradiated, it will re-emit in the infrared, and as it re-emits in the infrared, it'll actually start re-emitting at a slightly different location from where it's taking in the energy, and that re-emission actually applies a pressure to the object, and can actually get it spinning, and can actually change its orbital orientation. So it's really a case where solar radiation is affecting the orbital motion of an asteroid. So we don't study that directly, and it's not clear if the solar wind, it's actually kind of an interesting question, would the solar wind, for example, have an added pressure? And I don't know if anyone's ever really looked at that. So while the Yarkowski effect has been studied for solar radiation, for plasmas, I'm not sure the energy is quite the same level to cause that kind of motion.
And
it's an interesting question.
This is why we need people to keep going into science and keep studying science. There's so much that we just haven't had time to look at, and there's not that many of us. And so great questions are awaiting people to do great dissertations.
Right.
Now, so we have asteroids, that are actually getting smaller and under the effect of constantly having a few atoms at a time. Every 30 hydrogens, let's get rid of one silica. So it's a slow process. We have the moon. Now, Phobos and Deimos are in an interesting position because they're interacting with Mars and actually getting closer over time in one rather tragic case, unlike our own moon, which is slowly getting further away. So how do things look different when you start looking at this other pair of moons?
Well, it's interesting. One of my colleagues on DREAM, Andrew Poppy, actually has been looking at, and he's been working with Shannon Curry at the University of California at Berkeley, at how sputtering and plasma sputtering and the interactions are differ for Phobos compared to, say, our moon. And in particular, while Phobos is out in its orbit sort of ahead of Mars, it's getting interacted by it's interacting with the solar wind. However, when it gets behind Mars, it's actually getting energetic oxygen ions from Mars itself. And oxygen is a lot heavier. And these oxygen ions, as it turns out, can get accelerated down Mars's tail region, and they can actually hit Phobos and actually create enhanced sputtering. So what Andrew and Shannon have predicted is that actually, because of plasma sputtering, Phobos should actually have a neutral cloud, a neutral donut, a torus associated with it that surrounds Mars. Out at about 2.7 Mars radii, there you should expect a torus. And then what's more is that torus of neutrals over time will become photoionized. So there should be a sort of a region around Mars where there's like iron and all the kind of heavy metals from Phobos that are out in this donut torus around Mars from the Mars Phobos interaction, along with the Mars solar wind interaction. So they actually have two nice papers out just in this last year about this. So it's interesting that you asked that there is a difference because Mars is, the way to think about it is Mars is pelting it with these O pluses. And again, as these oxygens hit the surface shoots out its regolith material, like iron and aluminum, and that torus then will be filled with that kind of material from Phobos at the atomic level, of course.
Now, just to do another station identification for those of you who are tuning in, you are watching the Center for Lunar Science and Exploration Team Hangout. We do this about once a month, and we took off December for the holidays, but we should be back for the next 11 months. We are normally the first Tuesday of every month, but everyone's still recovering from the holidays, and we're so glad for all of you who've joined us for this special Wednesday broadcast. Now, if you would like to ask any questions, go ahead and give that little Q&A app a click, and we will get your questions to our special guest, Bill Farrell, who is with us from DREAM2. Now, we're lucky enough to live in an age where our limits are more budgetary than technological, and NASA has been able to put some atmospheric probes out beyond our own atmosphere with both LADEE and now with MAVEN at Mars. How are you able to leverage spacecraft to take the modeling work that all of your excellent people are doing and transform it into narrowing the theories down into an understanding of reality?
Well, that's a good question. I mean, models, if we don't have good inputs, then good data inputs, then the models themselves are just, it's sort of like garbage in, garbage out. So we really do need the inputs that MAVEN is providing. Like, I'll give you an example. As we study Phobos, we're going to do a number of us are doing a sort of a space environment study of Phobos coming up in April. And as we do that, we're going to need the MAVEN data to tell us what the plasma environment is to feed our models to help us um, understand, to help us, give us the starting point to get the products that our models would give us. So, some of the products include this prediction, like my colleague was doing, of this donut torus. But he needed, he'll need MAVEN data eventually to really refine that model. Right now, he only has really another model of the atmosphere. But as he gets the MAVEN data, now he can really refine that model of that donut torus that surrounds Mars.
And how exactly does MAVEN do this? Is it actually out there grabbing chunks of, well, not chunks, but grabbing samples of this high altitude material that's essentially orbiting Mars?
I mean, in essence, yes. I mean, they have plasma analyzers out there. And so what they are, these are electrostatic analyzers, and they basically analyze the plasma that's coming in and actually break it apart based on its electrostatic charge. Both ions and electrons. They have neutral gas spectrometers, which allow you to sense the neutral gases out there. They have magnetic field sensors and also radios. Radios are a great way to listen to the plasma, because when you start getting into disturbed regions, you'll start getting a lot more radio static in some sense.
And this is basically because you get radio light in the color of radio emitted when these different things are interacting. So just like we look at sparks with visible, we can hear sparks with radio, which is a color of light.
It's somewhat like that. Although really what's happening in the case of these lower frequency radios is, in theory, your plasma should have just as many electrons as ions to remain charge neutral. And if you stuck your radio into a perfectly charged neutral plasma at 0 degrees Kelvin, it probably would, it would hear very, very little noise. But what happens is, in reality, there's thermal fluctuations. There's also other disturbances, like when you go around the moon, the plasma has to flow around the moon. And what happens is you'll get temporary displacements of the electrons from the ions, giving rise to things like plasma oscillations. And your radio can detect these various oscillations and displacements in the plasma. And in fact, there's one particular displacement called the Langmuir wave, where if you think of your ions as heavy and immobile, your electrons are almost like on springs going back and forth. So there's a characteristic frequency, and that characteristic frequency is directly proportional to the density of the gas. So the plasma is actually telling you what your local density of your gas is. It's really kind of neat. Your plasma is, in some sense, calling out for you what its density is through the radio by this narrow band tone called the Langmuir wave, or it's actually called a plasma frequency emission. So it's handy to have a radio around, because it's another way to get a diagnostics of the plasma.
That's really awesome. And we're getting the question in, will OSIRIS-REx make any measurements of Bennu's exosphere surface that you're interested in?
Not exactly. It does not have the same type of packages that we're talking about on MAVEN. Unfortunately, of course they had to pick and choose, and they actually had their own objectives, which is to get a sample. It's going to have it's going to have various spectrometers to look at the regolith, but they won't be looking as much at the exosphere and at the plasma environment.
It's very much a go in, grab a rock, come back kind of mission, and that's actually a mission that I work with. And so tune in for CosmoQuest, admittedly in 2019, but we will be inviting you to help us map out the surface. And yeah, so get trained, get used to everything with Mars, Moon, Mercury, and in the future we will help go pick up a rock, which is going to be the most expensive picked up rock probably ever. But it's awesome. It's a space rock. So we're starting to run down out of time, and this has gone by so quickly. This is awesome. You don't think of atmospheres as being this interesting, and I hope we've changed a lot of minds with this conversation. If you wanted to help people understand how exciting everything you do is, what one piece of information would you want them to know?
That's a good question. I mean, good question. Where would you go in some sense? Where I think what you're asking is where would you go to find out more about this? Is that what
Well, no,
you're
that
saying?
was going to be my next question. It was the takeaway fact, that awesome thing, like for the work I
The most
do.
awesome thing is that the space environment has a direct effect on these exposed bodies. And so it's an action reaction. And again, let's go back to the carpet analogy. When you whack that surface, all kinds of material gets emitted, neutral gases, ions, and dust. So, if you think about this body just floating there, and, we always like to think of asteroids as dead bodies. They're not dead. They're actually animated by the medium they're immersed in. So that's, I think, the takeaway point is don't think of, space is not a vacuum. And these bodies at the atomic level are very active with gases hopping around, all kinds of interesting things going on at the atomic level.
And dust is going to be one of our great challenges in trying to figure out how to safely explore all of these different silica covered, charge covered objects throughout our solar system.
Right. There's one other aspect, and I didn't get a chance to touch on this, but I probably should, is that when the solar wind, which is really protons or a hydrogen ion, when they hit the moon's material is almost 50% oxygen, right? So the regolith material is silica, SiO2, iron oxides. So when hydrogen implants, it's interacting with an oxygen. And in 2009, some of our colleagues at Brown University and at JPL discovered that the moon has a veneer of OH and possibly water. So what's really to me interesting about this, once we've gotten into it, is that the moon may be a little water factory by its interaction with the solar wind. I mean, the sun is throwing out half of it. The silica provides the other half, and you can then make OH and create water out of what seems to be just rock. And it's just sort of amazing to think about that. What it does, it makes every inert, airless body, something that we thought of as dead, now having incredible potential to make OH and water just by simply holding it up into the solar wind. With those hydrogens at one coming in at 400 kilometers a second, 1 kilovolt per meter, a lot of energy coming in, slamming into that body. They now, some fraction of them are sticking around to make OH, hydroxyl.
The solar wind is doing a lot more than I think most people realize.
Right. So there's all kinds of weird chemistry going on there. That's just really cool. And that's just a real cool topic, again, that we're working on in DREAM.
So maybe we want to keep our spacecraft out of the wind, but always put our rocks into the wind to turn them into water.
Well, yeah, that's right. Something like that. It's the great equalizer. Even the small pebble now has the potency to make water.
Now, you have some great people working with you that are working to help make all of this understandable to anyone. I know Andrea Jones is the head of your education public outreach. She's someone that we've had on as a guest talking about the International Observe the Moon Night. Can you tell us quickly how people can go and take advantage of all of these amazing ways that your team has put together to learn more?
Right. Well, we have a team webpage that describes a lot of our work, and then from there you can actually link to SURVEY. Our parent organization is SURVEY, which is Solar System Exploration Research Virtual Institute.
Yes.
It used to be the old NASA Lunar Science Institute, and then they changed the name. Anyway, they actually from there you can link into our other 9 teams. So you get the DREAM2 perspective when you hit our website. But when you look at these other websites, a lot of terrific stuff's going on. And there's a lot of cross correlation. Like some teams are doing field work about, on what would happen when an astronaut starts roving around. And so we talk to them to get a perspective on and talk to them about charging and that kind of thing, so that they understand that could be, one of the issues they've got to deal with. Other teams are looking at other elements of asteroids. Other teams are looking at origins, just the origins of the solar system itself. So there's a very diverse portfolio, but oddly enough, there's a lot of common topics too across teams, like cohesion, dust cohesion. There's experts, I think, on a number of teams that work on dust sticking and dust cohesion, because that's what a lot of people think is how asteroids are all put together. It's really cohesive factors between the bodies.
Everything starts with that hit two things hard enough together and they stick together principle. And gravity only kicks in after it gets really big. So it all initially starts with the throw it together and see what sticks.
Exactly. That's exactly right. The van der Waals force is maybe the thing sort of holding some of these rubble piles, they call them, together, because they're the largest force, as it turns out. That's why we asked the question, what would then happen if an astronaut comes in and just touches this rubble pile? It only has got cohesive forces holding it together. It actually changes the definition of what a dust grain is. A dust grain may not be small anymore, might be a pebble, because it's now cohesively sticking to you like a dust would here on Earth.
Or I think probably a better, more tangible example is that you take a balloon and you rub it on a cat, and then you can stick the balloon to the wall until the air causes the charge to dissipate. But you don't have, for that asteroid, anything to dissipate the charge. So take a piece of asteroid, rub it on a now very angry cat, and you can stick it to another asteroid.
Right. You got electrostatic forces that dominate over gravity. You've got cohesive forces that dominate over gravity. So there are people on survey like Dan Shears and Chris Hartzell who've written papers about where does gravity tail off, and where do electrostatic forces and cohesive forces start to dominate. And of course, within asteroids, cohesive forces could be the thing holding a lot of these rubble piles together.
And I have to admit, this brings up my favorite vocabulary word in all of astronomy, and that's triboelectric effect. This is the go ahead, you explain it.
Well, yeah, that's exactly when you scuff across a carpet. That's triboelectricity. And it really has to do with grains of different material, and sometimes even grains of the same material coming together and rubbing and creating generating charge. And it's actually very common in volcanoes. It's what gives the volcanoes its electric charge.
Which is why you get thunderstorms.
You get thunderstorms. That's right. And actually, we've gone out into the desert and looked at dust devils here on Earth, and actually we found very large electric fields in dust devils at many tens of kilovolts per meter from triboelectric charge.
No. How do you measure that? I like have pictures of you chasing a dust devil with the electricity wand.
I will tell you what we've done. A couple different strategies. One is we've placed electrical sensors at a site and had dust devils pass, but not enough pass. So actually what we've done also on some of our campaigns is we've actually taken gear, put it to the top of our car, and we chase after them. So we'll take an electrometer. And actually the fields are large enough. You can actually take a fairly simple electrometer, put it to the top of your car, drive through it, and you'll measure an electric field, a large electric field associated with the dust, with the charged dust.
That is kind of awesome in so many different ways. Things that you never imagine that someone who studies asteroids is going to do. You do truly have an awesome job.
Oh, it is. I mean, they're doing that kind of work is pretty fun.
Cool.
Going out and chasing these things down.
So we have 5 minutes left. What one thing do you want the audience to walk away with, no matter what, tonight? And how do they find it?
That the environment at these bodies, at these exposed rocky bodies, is very dynamic, and that there's energy constantly coming in, and that there's a reaction. And I think that's the primary concept. And the way to start looking for this is looking on our DREAM website. In fact, if you Google GSFC DREAM, the very first link will be to our website. And there'll be information there, but then go up through survey, we have papers online, and you can actually start accessing those and getting a glimpse of what we do.
And I love one of the comments we have came in. It's I'm getting thirsty in reaction to the making water with the solar wind hitting silica. And I know I personally now want to remove all the carpeting from my house. The NSA does not need to hear your analogy.
There you go. That's right.
So it's really been a pleasure, and thank you all of us who are out there joining us live. I would encourage you to let others know about the show, and for those who didn't catch it live, you can always find us on our YouTube channel, and the audio will be going out, as I said, on the 365 Days of Astronomy podcast, which this year, since it's a leap year, is going to be going live for all 366 days of the year. So get your science and join us again next month when we will be coming back on our regular Tuesday night spot to bring you a little bit more about the NASA lunar explorations, and now also asteroids and Phobos and Deimos, because we like to collect random objects. This is the Center for Lunar Science and Exploration Hangout. I am Dr. Pamela Gay. I have had with me my fabulous guest, Dr. Bill Farrell, and it has been great, and I hope that we can have you on again many times in the future.
For sure. Thank you. Yeah, it's a lot of fun. A lot of fun.
Thank you.